All right, so 310, related rates. And this is just a strategy. You may or may not want to write this. I mean, I wouldn't write it down. You can go on and get the notes, and it's right there. Drawing a picture is helpful, and remembering that everything is related to time. Okay, everything's related to time. Remember when we did implicit differentiation, and you had different variables, and you always had a dy dx attached? Every variable is going to have a dt, something dt. If it's an x and you take the derivative of it, it'll be dx dt. If it's a y, it'll be dy dt. If it's area and you have a dA dt, radius dr dt. Everything is related to time. Because this is about rates. How fast is the rate changing? How fast is the radius changing? How fast is the volume changing? How fast is the ladder sliding down the wall? All of those things are rates. They're derivatives. So write down the numerical information that you're given. Write down what you're asked to find. You need to be able to read this and say, oh, it's saying how fast is the radius changing. So you're asked to find dr dt. So when it asks about a rate, how something's changing, it's a something dt. Okay? Then you'll write an equation that relates the variables. If it's talking about area of a circle, what would the equation be? Pi r squared. If you're talking about a ladder leaning against a house, yeah, the Pythagorean theory. You have x squared plus y squared equals c squared, z squared, whatever you want to call that over there. So, you know, there's something to relate all of these, all right? Then you're going to differentiate with respect to t, the whole thing, and then you evaluate it, okay? So that's just a strategy that will be helpful, hopefully. Questions? Nobody? All right, so let's look at these problems. They start out a little bit easier. Not too bad. Can you guys see that? I know I need a little bit bigger. All right. Suppose that a dimension x and the area a equals 12x squared of a shape, we don't know what that shape is, are differentiable functions of t. Write an equation that relates dA to dx dt. So, that might sound a little confusing. Let's take this equation and take the derivative of the whole equation. When you take the derivative of a, what do you get? That's 1a. So you get dA dt. Because remember, this is with relation to t. Equals, what do we get over here? 24x dx dt. Everything's going to have a dt with it. And so now, have we got the answer? What's going in the box here? Yeah. So that's what it's asking on that question. Does that make sense?
So it's just like everything we've been doing, you just put it.
Mm-hmm. Mm-hmm. They do get a little bit more complex. Oh, it's such a problem you're going to have. Okay, assume this one. We've got y, I think this is y equals, is this y equals x plus 2, I think? X squared plus 2. Okay, and it gives you the equation. It gives you dx dt is 5 when x is 2. Find dy dt when x is 2. So, let's write the equation. All right, let's take the derivative. So what do we get? Dy dt equals 2x dx dt, and what happens to the 2? Goes away because the derivative of that is a 0. All right, and so we're trying to solve for dy dt when x is 2. So dy dt equals 2 times 2, and what is dx dt when that? 5. So what's our answer? 20. Okay. Are we good? Y is what? Y is, I didn't hear your whole question. Up in here, it said dx dt is 5 when x is 2. Okay? You're just plugging it in. Okay. All right. Assume that all variables are implicit functions of time t. Find the indicated rate. So you've got this function, and you're given dx dt when x is 3 and y equals -1. Find dy dt. Okay? So right now, this is the forerunner of the word problems that we're going to have, because they're not going to say dx dt is this and whatever. You got to figure that out. All right, so let's write this equation. Whoops, in blue. All right, if we take the derivative, what do we get here? Plus good, equals 0. And that's important. You got to have that equals 0 there. Okay? All right, now what are we solving for? dy dt. So we've got to isolate that. So how do we start that business? Yeah, let's subtract this one. So we got 8y dy dt plus 2 dy dt equals -2x dx dt. All right, then you're going to, if you're solving for this, let's factor it out. Not equals. Oh, never mind. Is that right? Is that what I was doing? I got stuff to plug in, don't I? I'm not looking at the problem. dy dt equals -2x dx dt over 8y plus 2. Now, do we have some things to plug in?
Yes.
Somebody have that so I don't have to scroll up.
So it's
Hold on.
dx dt is 3.
Okay.
X is 3 and y is -1.
Y is -1. Okay, so we're just going to plug in. Bless you. Again. Okay, let's see what you get for that answer. What'd you get?
3.
Is it positive? Yeah, because it's negative. Okay. Yep. Okay, does that make sense? What we did? We solved it down to this part, and then we were given parts with numbers to plug in. We did that, and we got the value for dy dt. Questions? Anybody?
When I understand the initial y,
You want me to go back up to the problem?
yeah, like is there a rule or something that's allowing you to, like whenever you're doing the initial problem that's allowing you to put dx dt and dy dt behind each one of those? Does that make sense?
Well, you're implicitly differentiating, meaning we are differentiating with respect to time. So if you take the derivative of x squared, you have to tag on the dx dt. You have to.
Just for this type of
Well, because we don't, otherwise, the problems where you don't have to do that is when you have y equals something, and you're just finding y prime, and it's all on one side. But this isn't solved for y. This has other variables, and we're doing it with relation to t. So you're going to have to do that. Just know that in this section, you're always going to do that.
So how whenever like it wasn't y equals, I thought that you just included dy dt on the end whenever it was a y.
Right, that was the only variable we had, and we were doing it with relation to x. Now we're taking the derivative with respect to t. And so the x's and the y's or the r's and the a's, everything will have a dt hung on it. Okay? All right. Let's look at this one. This is where we got to do our own stuff. Let me make this down a little bit. Okay, a metal cube dissolves in acid. So just picture you got this cube, you put it in some acid. That's an interesting thought. Such that an edge of the cube decreases by 0.40 millimeters per minute. Decreases, and then you have a rate. So is this a dt?
Yes.
Yeah, so that's going to be a dt. That's a derivative. How fast is the volume of the cube changing? Is that a derivative? How fast is the volume changing? That's a derivative. That's a rate. When the edge is this amount. So, what do we know? Let's do this. And I'm not an artist, but something like that. I don't know.
Oh,
Whatever. Okay. So that's a cube, or supposed to be, and we're going to call, do you know what the volume of a cube, what would that be? Well, aren't all the sides equal in a cube? So if we called this S, what would the volume be? S cubed. Okay, so that would be an okay equation for that. All right, and so we're saying this edge decreases by this amount. So what is this 0.40? Could we call it ds dt? If this is S and it's changing, it's decreasing at a certain rate, would that be fair to call it ds dt? And whenever something is decreasing, like if you have a snowball melting, if you have this thing decreasing because it's being eaten up by acid, does it make sense to make that negative? Because that side is getting smaller. If it were a balloon and it was being inflated, the volume would be increasing. That'd be a positive change. This is a negative. Okay, so we want to write that down. All right, what are we supposed to find? How fast is the volume of the cube? Okay, so volume of the cube changing. What rate are we asked to find then? Find dv dt when S is equal to 7.90. So we've drawn our picture, we've written what we were given, and we've written what we were asked to find. Does that make sense so far? All right. So here's our equation that we wrote that relates all these things. We have a volume, we have a side. Let's take the derivative of this equation. We have dv dt equals what? 3s squared ds dt. Okay? We're asked to find this when this is 7.90. And we know what this is, right? Okay. So, let's fill in. dv dt equals 3. S is 7.90. And ds dt is negative 0.40. So you do the math on that one. Calculator. And it does say round to the nearest integer as needed. So let's see what you get. What?
75.
What did you get for before you rounded it?
Negative 74.
Okay? And
But
so
wouldn't it be positive because you don't have a negative volume?
this is a rate. The volume is not negative. The rate that it's changing, it's decreasing. Because as that side melts with the acid, the volume has to decrease. So it's the rate at which it's doing. It's a negative 75. And it has the unit there, millimeters cubed per minute. Okay? Are we good? We still, did you get that? Or no? 7.90 squared times 3. Oh, didn't square it? Okay. All right. So we're good?
We're good.
Okay. All right. Number 5. Number 5, the dimensions x and y of an object are related to its volume by the formula. So we don't know what object it is or anything. It's just v equals 3x squared y. Now, this is kind of an important concept. It asks you some specific things. How is dv dt related to dy dt if x is constant? So if this is a constant, think about that. Let's take the derivative all the way, okay? What do we get? If I could write right. And then, sorry, you're not quite right. Is this a product? Yeah. So, what do we have? We have 6x, well, we'll do it that way.
3x squared dy plus y, or 6x y, or dx.
Y. Okay? So does everybody agree now that we've got that? All right. You were tricky. Okay. All right. So, yes? Lee? Question?
You come up with the 6x. Yeah.
Over here?
Yeah.
Take the derivative of that piece,
It's a product.
because this is a product. So 6, 2 times 3 is 6x dx dt times y, because you're not taking the derivative of y there.
I thought it was derivative. Okay.
It's 2 pieces. I skipped something? I didn't do the road map.
No, I'm not confused.
Okay. It's this piece times the derivative of that. Oh,
Is it like out of order? Like, I mean, like from the first times the derivative of the second plus the second. I just did it backwards.
I just didn't. I did. Sorry. So sorry. Okay. Complete the equation for when x is a constant. When x is a constant. Well, if it's a constant, and this is y, I just want you to think about this. If this were like 6y, what's the derivative of 6y? 6. So if this is a constant, what's the derivative of this? 3x squared? That's the constant. Does that make sense? Sometimes you have to let things be other things, and that's what this is getting ready for. All right, what if y is constant? If that's constant, then what do we have? If this is constant, 6xy.
So wait, you just throw the y out?
Well, if y is a constant, it's something that stays connected to that. And so up there, if that's a constant, it's like another number, right?
So for like A, you just put like y as 1.
Well, put y as 1? No?
Instead of your constant.
Yeah, if y were a number, if it's a number, the derivative of it is what? The derivative of it's 0, but if it's a constant, it's going to get, okay, right here, let me just go back to this. If x is a constant, then all we have to worry about is taking the derivative of y. The derivative of y would be 1, right? But this is a number in front of it. This whole thing is a number. We're playing like. And so think about 6y. The derivative would be 6, right? dy dx. So 3x squared is a constant. That's the derivative.
Okay.
Does that make sense?
Yeah.
And then this one, when y is a constant, so say you had 3x squared times 5. Doesn't that become 15x squared? But we don't know what that number is, but we have 6x, because we know what that is, and it's going to be multiplied by this number. Does that make sense? Sort of? It's kind of crazy. All right. How about when neither x nor y is constant? Is that what we had up here? So we would have 3x squared there and 6x there. It was trying to make you think. It was trying to get you just outside the box a little bit. Okay? How dare it. Of course, I did pick the question. Okay. All right, so we're good? All right. Whoa, go back. Do what? You're good? You're still writing? Okay, you're good. Keep writing. Do I need to go up higher? Are you good, Lee? Are you good, Emma? You're good? Okay. All right. Time for you to try one. Time for you to try one. When a circular plate of metal is heated in an oven, its radius increases at a rate of this, 0.04 centimeters per minute. Here's your clue. That's a rate. At what rate is the plate's area increasing when the radius is 46? Okay? Can you read those back there? This is 0.04 centimeters per minute. That's the radius changing. And that's 46 centimeters is when the radius is that. Area of a circle is pi r squared. Yeah, you were thinking circumference probably. Perfect. What are we trying to find? How fast the area is increasing. So what is that called? dA dt.
Wait.
Okay, so we were given. I'll let you keep working.
It's asking for the exact value of pi.
When it says
So it's
exact,
like-
increase pi, you read pi.
So I should just
Do the numbers and then leave it with pi. When you read the question, you want to be sure and read the parentheses instructions, type an exact answer. If it's exact, you leave pi in the answer. You don't, substitute the pi key. You don't use 3.14. You leave pi in the answer. Yeah, don't substitute anything for pi. Leave pi as part of your answer. Okay, did we get that? Mm-hmm. Right here. So, you were given how fast the radius was changing. You were asked to find how fast the area is changing. You should know the area formula for a circle. I will tell you right now that you probably need to know that formula for the test, so write that down somewhere because you're going to have it in front of you. There's a couple of other ones I would know and look them up. Volume of a sphere, 4 pi r cubed, I believe. Surface area you need, and I think that's something square,
4/3
pi r squared. Yeah, so volume and surface area of a sphere, you need those. Possibly a circle area.
So surface area is just 4/3 pi r squared.
I think it is.
It's 4/3 pi r cubed, and then the area is 4 pi r squared.
Is it
What's
that?
the derivative of the other one? The other is just 4/3 pi r cubed, and then the other one is just...
Okay.
Yeah, you're right.
Don't take my word or his. Just look them up. Jeremy and I were conferring, and we were agreeing. So I don't use it every day. Look them up. Okay? I'm telling you, if I were giving it to you in class, I would give you those formulas. But you can look them up. Okay? All right. Any questions on this one? Yeah? Okay.
That should come up with 3.68.
Did you do 46 times 0.04 and times 2? Did anybody else get that number?
Yeah, I got it. You just times the 2, that's 46, and it's 0.04. And
You just leave
you leave
pi.
pi.
Yeah. Is that what you did? You were using something for pi? Okay. Because it said this, Leland, because it said this,
So you just...
leave pi in there. All right. We are now going to do Lucas's favorite problem.
I'm not even going to look at it. Pi r cubed and 4 pi r squared.
Okay, so 4/3 pi r cubed is the volume of a sphere, and 4 pi r squared is the surface area. Lucas, that was right? 4 pi r squared is the
The
surface?
surface area is the 4 pi r squared, and the volume is the 4/3 pi r cubed.
Okay. All right. So we're good. All right. A 13-foot ladder is leaning against a house, and its base starts to slide away. So the base of the ladder is moving away. By the time the base is 12 feet from the house, the base is moving away at a rate of 10 feet per second. So by the time it gets to that 10 feet or 12 feet, it's moving at a rate of 10 feet per second. Wants to know 3 things. What is the rate of change of the height of the top of the ladder? Because what's happening with that ladder? As it goes this way, what's happening to the top of the ladder? It's sliding down. So it's saying when it reaches here, how fast is it sliding down at that very moment? That's a derivative. At what rate is the area of the triangle formed by the ladder, wall, and ground changing then. Okay? Area of a triangle. Do you remember that formula?
Base times height.
1/2 base times height. You might need that one. Area of a triangle. 1/2 base times height. Okay? Geometry never gets to leave us. You engineers, you should know
Wow,
those.
that is
Yeah.
base times height divided by 2.
Oh, that is the same thing. Yeah.
Yeah.
Okay. And then this is kind of a twist in this question that you didn't always see in high school. At what rate is the angle between the ladder and the ground changing at that point? So there's 3 things in this question. Okay. All right. So we already have a picture, but I'm going to draw a little bit bigger picture. Okay. This is going to be your theta. Here's our 13-foot ladder, and I'm going to call this x and this y. Okay? All right, what do we know? What do we know this value is? Because we're talking about a certain point when x is 12. Okay? And this is the thing. When the base of the ladder is changing, they gave us a rate. The base is moving away at a rate of 10. So could we say that dx dt is 10? Okay. And it's moving that way positively, so we're going to leave it positive. All right. Is there a way to know what y is when x is 12?
Wait, what did you say dx?
Just do
Why is it this?
It says here the base is moving away at the rate of 10 feet per second when you're at 12.
Oh.
So dx dt is 10 when x is 12. So we also need to find out what's y equal to when x is 12. No? You have 12 squared plus y squared equals 13 squared, but you really should remember there's that special right triangle, 5, 12, 13. Anytime you have 12 and 13, that other piece is going to be 5. Okay? Okay. Because you'd end up with y squared is 25 and y is 5. So, now we have that. Okay? So we got that, right? Okay. What kind of relationship do we know in a right triangle? We just kind of wrote it there. So let's write that here. X squared plus y squared equals, we'll call it c squared. We can call it whatever we want. Let's put in here 13 squared. Okay? I need a whole lot more room. Okay. So if I put that in, oh, that's the ladder. The ladder's 13. All right, let's take the derivative of this. Take the derivative of this, because we need some dx dt, some dy dt. We need some of that stuff. So what do we get when we take the derivative?
2x dx dt plus 2y dy dt equals 0, 0.
Mm-hmm. Okay. Do we have a lot of those pieces? We know an x, we know a y, we know a dx dt. What do we not know? And isn't that what this is asking for here? Okay. So let's plug in the numbers that we have. 2, what's x? 12. And dx dt? Plus 2, and what's y? 5. dy dt equals 0. So 240 plus 10 dy dt equals 0. 10 dy dt equals negative 240. So dy dt is what? All right, does that make sense that it would be negative? That top of that letter is sliding down. So that's what that is. So that's your dy dt, negative 24. Okay? What was the next part? What did the B part say? The area. How's the area changing at that time? So let's go right here and talk about the area. What did we say the formula was? 1/2 base times height. Well, what's our base? X, y. So let's just write 1/2 x, y. Okay? Okay, so we got to take the derivative. dA dt equals 1/2. I'm just going to put the 1/2 on the outside. Do we have a product?
Yeah.
Okay, so what do we got? We got x dy dt, y dx dt. Do we have all those things? Okay. 1/2 times, what's x? 12 times negative 24 plus what? How is it 12? X was 12 up at the original, ma'am. What's y? 5. And what's dx dt? 10. So let's see what you get.
I would have probably messed up already because I thought we were doing dA or dt equals 1/2 x dy dt.
Mm-hmm.
I would probably put x dx dt because that's what I'm doing.
Well, but look here, Leland. This is a product, so it's x times the derivative of this.
Yeah, I got it.
Okay.
Yeah, but what, I'm just wondering, why did the 1/2 go anywhere and everything get rid of it?
Well, we can get rid of it. It's going to get multiplied by all this.
I know, but why wasn't that included
The derivative?
Yeah.
Well, because you've got a product. You've got a number times the product. I mean, you could say that's 1/2 x times y, and you could do it that way. It'll still be incorporated because it's going to just be multiplied. Okay? Doesn't make sense? Does somebody have a number? Yep. Okay. Are we good? Lucas, is this bringing back wonderful memories for you? Okay. Make it go away. We have one more part, the fun part. All right. Now it wants to know how fast is the angle changing? Radians per second. Okay. Okay. What do we know? We're going to have to use our trig. Okay. So I'm going to come down here and give me some more room and write that triangle again so we can see it. Oh, that's a bad triangle.
It seems to be hard for credit on the
Yeah, maybe I should give you 3 hours. I don't know.
Wait, just not put this one on the test.
Oh, it's already there. Okay. All right.
You don't start till second one.
That's true. Okay. Do you agree?
Yes. No.
Whatever the ladder is. X over the ladder. Did I write this backwards? I don't know. I guess that's right.
Yep.
Okay. This is X, and this is L. Do we agree with that?
Yeah.
Okay. Let's take the derivative of both of those signs. Assuming, let's leave X as X. Let's think of L as a number. Okay? We're just going to think of it as a number, not a variable. Does that make sense? For right now? Trust me? All right. What's the derivative of cosine? So negative sine theta equals, and if you think of this as 1 over Lx, what would the derivative of that be?
1 over dx.
Dx dt? Oh, and I forgot that over here.
I got that.
Sorry. Okay, because isn't that what we're looking for, d theta dt? Yeah. All right. So, do we know the value of the ladder? And do we know dx dt? Okay. What is the sign of this theta? 5 over 13. So I've got negative 5/13. This is, I'm plugging in. D theta dt equals 1 over 13 times dx dt was 10. So if I'm solving for d theta dt, what do I do with this guy? Multiply by reciprocal. What do I get?
Would it be negative 2? Oh, I know. It's still
Negative 2 radians per second. With that problem. With that problem, yeah. Okay. We good? Yes, sir.
Alright, so you're saying that the ladder's going to fall, what was the answer?
Well, the top of the ladder is moving at negative 24.
What if a 200-pound dude standing on top? Does that change the speed that it's moving? And so, how would you figure that out? Like, when does that come into play?
I don't think you'd actually, I mean, you might have, I mean, because that's all about gravity and weight and all of that. I don't think you're going to see a problem like that, but you might, I haven't seen one where.
So is that assuming no gravity?
Well, it's just assuming normal gravity with no weight on it. I mean, it's just because this part of the ladder is going, it's automatically pulling this at a particular rate. And you're not, with calculus, what you're doing is, it's all about instantaneous rates. So when this is this far, it's changing at a rate, and this is changing at a rate. They may or may not be the same thing. But that's what we're talking about. How fast is that thing changing at the moment that the bottom of this is 12 feet away? But we don't typically have, you know, a man sitting on it or whatever. At least I don't work with those. But I'll look for a problem like that just for you. Not for you to work, but I'll see if I can find that. All right. I would like you to try this one. Because I have decided to take number 9 out of the homework. It's really long, and you guys
So
are...
we shouldn't get on the homework till tomorrow?
Oh, I'll do it before I leave.
Oh, that'll be...
So you can get it on it. Yeah. I'll just take it out. You already got on it? That's fine. All I have to do is make a copy of it. And you didn't do anything, did you? On it? You did? Okay. We'll talk. All right. A balloon is inflating with helium at a rate of. How fast is the balloon's radius increasing at the very instant that the radius is 3 feet? And then how fast is the surface area increasing? Okay. Cute balloon. So the balloon's getting bigger, right? And so it's inflating at a rate of, excuse me, so what's changing? What's changing? The volume. Okay, so you need to write down what you're given and what you're asked to find. You have 2 parts to this. This is really good practice for the test.
Which means this one's not.
AKA I made up problems for my AP Calc, and one of them was the students were throwing a snowball at Ms. Barnes, and they so loved that problem. And the snowball was melting at a rate of whatever. Yeah, we got it.
is weird because you did the derivative of this, did it give you surface area?
It does. The derivative of the volume, and that's what Lucas was saying. That's how he remembered them. It is weird. How fast the radius is increasing.
Wouldn't you have to have 144 pi? That's what you had.
Yeah, sorry, thank you. I count on you to catch my little forgetful things. And that was feet per minute. Does that make sense? The more you do of these, the better they are. And then you got to do the surface area. Did you already do that? Mm-mm. 4 pi r squared. And that rate is feet squared per minute, but it's given in there.
So, the S equals 4 pi r squared, is that the...
Surface area formula. Mm-hmm. Okay, what I will tell you, and number 9 is, number 9 is such a good problem. But, and I am going to take it out just because you're so tired, whatever. Here is the work for it. It's not a bad problem to study, to look at. It's not on the test.
It's not a lecture.
But that's the work for it. I would look over it. I don't think I didn't put it on the test. So it's okay. I am not telling you. Let's just end this.